Students, this is a third class on the mechanics of solids module 3. So now we are going to study about the shear force and bending moment diagram of simply supported beam. That is, last classes we have studied about a cantilever beam. Cantilever beam, a beam which is having a support at only one end. An example, it is a sunshade beam. That is an example of a cantilever beam. Now we are going to study about a beam that is a simply supported. That is, both ends are having supports. So a simply supported beam, it is mainly denoted like this. So we will be having two supports. Now we have to, here a different type of loading will be coming. So how we can draw the bending moment diagram? That is a thing which bending moment and shear force diagram we are going to study. So I'm straight away taking one example problem. That is, I'm considering a beam like this. Here it is having a 5 kilonewton load. Here it is having a 10 kilonewton load, and the beam, the span of the beam is 5 meters. So I am taking a 1 meter, 3 meter and 1 meter. So total a 5 meter beam is there. So I have to find out the shear force and bending moment of this beam, and also have to draw the bending moment and shear force diagrams. So this is the discussion which we are going to do. Okay, so here first of all I am just marking the beams as RA and RB, A, B. Here the points A, B, C, D. These are my points. Okay, sometimes these will be given. The first thing is that you have to find out all the forces coming in the beam. So here we are having two vertical forces, 10 kilonewton. These are the forces that are acting in the beam, and due to this forces there will be reactions. That is, reactions at the supports. Therefore there are two reactions. I am marking these reactions as RA and RB. So here my first step is to, step 1 is to find out the reactions. Okay, that is, I have to find out RA and RB. I have to find out RA and RB. So I can use the equilibrium equations. You know that what are the equilibrium equations available? That is, sum of the vertical forces can be 0, sum of the horizontal forces should be 0, and the moment at the point, some points will be 0. These are my available equilibrium equation. Using these equations I can solve this. So here I am having two unknowns, RA and RB. So I need two equations. So here first of all, here we are having vertical forces. So I can use the first one, that is sigma V is equal to 0. So I am using this equation, sigma vertical forces is equal to 0. So what are the vertical forces acting? RA, RB is there, 5 and 10 is there. So I can write the sum should be 0. That is, RA and RB are taken, it is in the upward direction. So it should be like this: RA plus RB should be equal to 5 plus 10. 5 plus 10, that is equal to 15. That is the first equation. Next one, it is, so since there is no horizontal force, I cannot use this equation. Sigma H is equal to 0 cannot be used. Now I have another equation is moment can be, I can check that whether the moment at any points is 0. So for a simply supported beam, you have to understand, this is an important thing, that is, for a simply supported beam, the moment at the ends will be 0. That is, sum of the moments about the point A and sum of the moments about the point B, that is ends. These ends, the moments will be 0. Okay, so now I am having, so first I got an equation, now I am having another two equations are also there. So I can either take one equation or the other. So I am here I am choosing sigma MA is equal to 0. I am just taking that equation. Okay, so this is the thing. So here while considering, here first of all I am taking the moment from this point. I am considering the moment from this point. I am just drawing the line of action. So from here you have to know what are the forces acting. So moment means, what is moment? Moment is equal to force into perpendicular distance from the point of consideration. Okay, so the point of consideration here is A. So from here, which are the forces? There are only 4 forces: RA, RB, 5 and 10. In this, what is the RA is acting at the point only. Therefore, the moment due to RA will be 0. That is RA into what is the perpendicular distance? It is at the same point. That is 0. The next one it is 5. Next, the first moment RA, that will be 0. Next one due to 5 kilonewton. So 5 kilonewton is acting like this. So now, so just consider I am taking from here. This is the 5 kilonewton is acting like this. And how it will be rotating? It will be rotating like this only. It will be rotating. If I am taking a pointer and it will be rotating like this because it is in the downward. So it will be rotating in the clockwise direction. So what is the moment here? 5 into perpendicular distance. Perpendicular distance is 1 meter. Therefore, first one it is 5 into 1. Next one 10. So this is my perpendicular distance for 10. Again, it is also also rotating in the clockwise direction. Okay, also rotating in the clockwise direction. So that will be plus 10 into what is the perpendicular distance? It is 1 plus 3, that is 4. Okay. Then again, next one it is RB. So this is RB. RB will be the arrow is towards the upward side. So it will be rotating in the anti-clockwise. So I am anti-clockwise direction. Therefore, I have to take RB into what is the total distance? RB into 5. That is equal to 0. Okay. Therefore, by solving this, I will be getting that is 5 plus 40. That is 45 divided. So RB is equal to, it will be 45 divided by 5. Okay, that is RB is equal to, we will be getting as 9. RB is equal to 9. Therefore, RA is equal to, RA from substituting in this, I will be getting 15 minus 9, that is equal to 6 kilonewton. So RA and RB I have obtained. Okay, so the first step while drawing the shear force and bending moment diagram for a simply supported beam is that we have to find out the reactions. Okay, in the cantilever beam, it was able to directly find out the bending moment diagram without, because only one support was there. But here, in the case of a simply supported beam, or in the case of any other beams which we are going to study, the first step will be you have to find out the support reactions. So now I am just drawing the figure with the loads. With the obtained loads, I am just drawing. So here I am having these many loads, and here RA is 6 kilonewton. So here it is 6 kilonewton. Here it is 9 kilonewton. There is 5 kilonewton and 10 kilonewton. Okay, so this is the all the loads are coming. Now the step 2, it is first, now we are going to find out the shear forces. So shear force, I am starting from this point A. So I am now here I am starting from this left end. Okay, you can either take the left or right end, and just going through to the sign convention, as which we have earlier discussed yesterday. Once again I am taking the sign convention which we are following in our class. This is a sign convention, that is here. That is, if the left of the section it is moving upward, it is taken as positive, and right moving downward is taken negative, then vice versa in the case of. Okay, so just for a simply supported beam, it is easier to start from this end. Okay, I am starting from this end. So here from this end, if I am considering this section, a small section here, so here the RA, it is in the upward direction, that is in the left side. If I left, only one load is there, so I am considering a small section to the this here, a small section. What is the load to the left? It is in the upward direction, so this is positive. Therefore, I can write the shear force at A is equal to 6 kilonewton. Okay, shear force at A is equal to 6 kilonewton. Now, what will be the shear force between A and C? If I am considering a section like this. Okay, so I can either take the forces to the left, or I can either take the forces to the right. Left and right again. If I am taking to the right, what is the force? Only 6 kilonewton is, it is upward. Therefore, between A and C, what is the shear force? That is 6. If I am taking left, it is plus 6. Between A and C, it will be 6. Okay. And again, you can either, this is considering the left of the section. Okay. Now, if I am considering the right loads, right. So, considering to the right, what are the loads in the right? That is 5 kilonewton, 10 kilonewton and 9 kilonewton is there. So, either you can take to the right or left. So, if I am considering the right of the section, just understand what are the loads coming. So, left we go to 6 kilonewton. Right I am taking. So, what are the loads? So, right, the sign convention is again you have to understand if the right downward is taken as positive and upward is taken as negative. So, so downward it is positive. So, what are the loads in downward? 5 kilonewton is there, 10 kilonewton is there, 5 plus 10, then 9 is upward. So, what will be the answer? It is again 6 kilonewton. So, just understand here and here, if I am taking the left or right, the shear force will be the same. Okay, just to understand that only, I have just written this. So, just anyway, since there is no loads between A and C, it will be a constant only. Okay. Now, next one is shear force at C. So, shear force at C is equal to, I have started from this end only. Since only one load is there, therefore, now I can take, that is 6 minus 5, that is 1 kilonewton. So, plus 1 kilonewton, it is in the 6. Then, next one, shear force at D. Here again, it will be 1 kilonewton only. Then, shear force at D. What will be the shear force at D? So, I am considering to this, again, to the, at D, a 10 kilonewton is acting to the downwards. Therefore, 1 minus 10, that is minus 9 kilonewton. That is the shear force. Okay, that is the shear force at D. And again, when we are coming into the shear force at B is equal to, the shear force is again, it is written as minus 9 only. Okay, because just understand, here only one load is there, that is minus 9. So, likewise, we have found out the shear forces. So, now just I have to draw the figure, just draw the baseline, and from this end I can start. This will be very easy. So, here it is 6 kilonewton. So, 6 kilonewton is there and it is constant up to C. After reaching C, I am having a 5 kilonewton to the down. Therefore, this is 6 kilonewton. Again, it will be coming to 1 kilonewton here. Again, it is a constant and it is going up to here. It is 1 only. From here, and a 10 kilonewton is acting downward. Therefore, again, I will be going down. That is, again, this is 1 kilonewton. This is 9 kilonewton. Again, I am coming here. Again, it is same 9 kilonewton is there. For I can join like this. So, this will be my shear force diagram. So, here you can understand there are two regions. That is, one is positive shear force region and there is negative shear force region. Okay. So, it is very easier. Even by looking this figure itself, you can draw, because you just understand. I have found out, first one I have found out the reactions RA and RB. So, the reactions RB found out. Then from this end you just start. Then 6 kilonewton is there. Then it is going here up to here, it is 1. Then 1 is coming here. Then here in the CD region it is 1 only. Then again. So, likewise we can find out the what will be the shear force that is acting at the various points in a simply supported beam. Okay, so it is a very easier to draw the shear force diagram. Just to find out the reactions and then start drawing from the for a simply supported beam, it will be better to draw from the left side. Okay, for the other one, draw from the free end for the cantilever beam. Okay, so that will be easier. So like that, I have drawn the shear force diagram. Okay, now next one. So the only thing you have to write the steps is, first step 1 it is write the reaction. Then step 2, just write the shear force at various points. Okay, now the step 3 it is, now we have to find out the bending moment. So step 3 it is the bending moment. Okay, bending moment. So bending moment, again we are having different points. Here A, B, C, D, different bending moment, different points are there. And here we know the bending moment at A, that is bending moment MA, again denoting as MA is equal to 0 and MB is equal to 0. Okay, because the bending moment at these both ends are 0. So I am just marking that one first. Here I am having the bending moment at A and B is 0. Now again, now I have to find bending moment at under these loads also I have to find out. That is C and D. So first one I am going to find out the bending moment at C. Bending moment at C. It is not 0. So this is my point. Okay, this you have to clearly understand. So here this is my bending point C. Now here either I can take the forces to the left or I can take the forces to the right. That is, for example, I am taking bending moment that is to the left. I am taking left. Okay, left I am. What are the forces to the left? Only 6 kilonewton is there. That is, and it is acting in what direction? This is, so this will be rotating. You have to understand how it will be rotating. So this rotation, that is, if I am keeping a pointer like this, okay, a pointer is applied, and this pointer is pushed by this force. So how will that pointer moving? It will be moving in this direction. That is in the, what is the direction? Clockwise direction. That is, so what is the moment that is happening? 6 into perpendicular distance. That is 6 into distance is 1. Okay. So that is 6 kilonewton meter. And next one, it is a sign convention. So just understand here, when considering, here just understand, here we are having, this is a section I am considering. Okay. And here if the this is right and left. If the right of the section is positive, if it is clockwise, sorry, to the left of the section is clockwise, here it is clockwise, that is positive. Or if the right of the section is anti-clockwise, it is positive. This is the first one side convention. And if the left of the section is anti-clockwise, it is negative, and clockwise it is, and the right of the section is clockwise, it is negative. Okay, so this is the thing which we have done in the other cantilever beam also. So here we are now considering a section, and the section we considered here is the, what is the section we consider? This is the section C. C is the section, and here the left of the section we have considered, and how the moment is happening? It is in the clockwise direction, so it is positive. That is, this is plus 6. Some of you may be having a doubt. We can take the right. So I am just taking the right also. Okay, I am taking right. So whether I can check to the right what are the loads which are coming. That is 9 kilonewton is there and 10 kilonewton is there. So first of all I have to understand what is a sign convention. That is, right is anti-clockwise, it is taken as positive. Right of the section is taken anti-clockwise, taken as positive. So here first load is 10 kilonewton is there. How the 10 kilonewton will be moving? It will be moving to the downward. That is clockwise it will be moving. That is negative we have to take. Therefore minus 10 into, what is the load? The distance, that is 3 plus other, it is 9 kilonewton will be moving in the upward direction. That is anti-clockwise. That is 9 into, what is the distance? That is 4. So what will be the answer? 30 minus, we will be getting as 30 minus 36, that is again 6 kilonewton. So this is the thing. Right and left we will be getting the same answer. Again it is positive. So MC we have obtained as, I am just marking the point as, here it has 6 kilonewton meter. Okay, 6 kilonewton meter. That is the point. Now next one, it is MD, that is this section. I am considering this section MD. Okay. Now again I can either take to the left or either take to the right. So first thing you have to keep in mind is that it will be always better to take a section where the number of loads are less. That is, for example, here I am taking to the left. Then what are the loads coming? 6 kilonewton is there, 5 kilonewton is there. Again calculation is increasing, but to the right only 9 kilonewton is there. So that is your choice. You have to understand. So here I am taking to the right of the section. So you have to write here in bracket MD right, that is equal to. Now what is the sign convention? If the right is moving anti-clockwise, it is taken as positive. So how can, so if I am taking a pointer here, and how the pointer will be moving, this is pushing the pointer to this direction, upward direction, so it will be moving like this, that is anti-clockwise, that is positive. So positive 9 into 1, that is 9 kilonewton meter. So I am marking here as, so the point is marked as, so here it is 9 kilonewton meter. So I have got the points. Now I have to join. So in order to join, we can either join by straight line, we can join by parabola, we can join by cubic, etc. But here first you have to understand what is the loading. Here the loading, it is a point load. So a point load, here here the shear force diagram, you just understand it is constant line. So corresponding to that there will be only a linear line. So we can join like this, that is by straight line you can join. Okay, and the moment is positive. For this is a most of the time this will be a positive moment. So this is the bending moment diagram for this figure. Okay, so bending moment diagram we can obtain like this. So we have started to draw a shear force and bending moment diagram of a simply supported beam. So the first step is that you have to find out the reactions. Second step, you can find out the shear forces, then draw the shear force diagram minimum. So just understand that you can see that I have drawn the figures in the one below the other. So it is all, and try to always do it in the same page itself, so that it will be very easy to understand. Okay, when you are writing for the exam or etc., you should draw it in the same page itself, and the steps you can write it to the right side. So just draw the figures to the left, and you can writings only, some small writings are only coming, so you can just write in the right side of your paper. Okay, so this is the way in which we can draw this figure of a simply supported beam. Okay, so likewise here some problems are given. So I'm just okay. So here, so I have now done a main problem. Now here, just understand, here a simply supported beam is there, and a constant load W is acting at the center. Okay, load is acting at the center. Now the if W, it's a symmetric loading only. That is, here a load is acting W is acted at the center. So what will be the reactions? Since this is symmetric, therefore it will be W by 2, and here also it will be W by 2. So I am starting from this end. So I can draw like this, W by 2. It will be constant up to this point. Again a W is acting, so it will be W by 2 minus W. That is minus W by 2, and likewise it will be reaching here. Okay. So this is the shear force diagram with a central point load. Okay. Now the bending moment diagram will be like this. That is, so the bending moment diagram for a concentrated load at the center will be like this. That is, here the bending moment is 0. MA and MP is 0. Then what will be the bending moment at C? Bending moment at C will be either I can choose to the left or to the right. So what will be the bending moment? That is W by 2. If I am taking to the right, so that is the my pointer. The pointer is like this. Okay, this pointer, and this force will be pushing the pointer like this. So it will be pushed to the clockwise. Therefore, it is positive. For W by 2 into W by 2, L by 2. L is the distance. This is the distance, L by 2. So what is the moment? That is WL by 4. So this value you have to understand. So for a concentrated load at the middle, the value of the maximum bending moment will be WL by 4. Similarly, for if a load is acting like this, the maximum bending moment will be WAB by L. WA into B by L. So I will just sum of these two. These are just simple things. Three conditions you have to understand. These values you have to understand. That is, if I am having a simply supported beam like this, W, and its reaction, it is in the center. Now here the bending moment, maximum bending moment, the bending moment diagram will be like this. The center, this so this will be the bending moment. This value will be WL by 4. This you have to keep in mind, WL by 4. Now the second case it is, I am having a beam. Here W is acting. Okay. Okay, W is acting. This distance is A and this is B. So first of all I can find out the reactions. Okay, so the reactions, it is W B by L and W A. Here the reaction will be W B by L and here the reaction will be W A by L. Okay, it is you don't have to by heart this. So I can take the moment. From that I can easily find out. That is, I am taking here RA and RB. So what is the reaction? This is if I am taking the moment about this point A, then sigma MA is equal to 0. Okay. Therefore, what is the moments happening? W into A minus RB into, what is RB into L is equal to 0. Therefore, RB is equal to WA by L. Similarly, RA is equal to WB by L. Okay. And here the maximum moment will be here under this load. And that value of this value will be, I can find out the value. What will be the value? Either I can take to the left or to the right. I am taking to the right. So W into A by L into B. So the maximum moment value is W AB by L. So these values you have to understand. So WL by 4 and WAB by L. Okay. Similarly, there is another condition also. That is, I am having a beam. Now we have understood how to do the with the point load. Now I am considering another type of load, that is a concentrate UDL, uniformly distributed load, UDL. Let this be this value be W kilonewton per meter. I am just generalizing only, kilonewton per meter. This is the total length L. So I have to find out the bending moment diagram and the shear force diagram. So here I am taking A and B. Okay, A and B is taken. First of all, I have to find out the reaction. So what is the reaction here? That is RA and RB. Okay, so here reaction I am taking. So I am having RA plus RB is equal to, what is the total load? W into L. That is the total load, because it's a rectangle load. For the area will be the loading. That is RA into RB. Now next I am taking the moment. That is moment about A. That is moment about A and moment about B will be 0. Sigma MA should be 0 and sigma MB should be 0. That is a simply supported beam. A simply supported beam only. So I am taking sigma MA is equal to 0. That is taken. So again, what are the loads? One is this, the moment will be due to this UDL and due to this upward force. So due to this load, due to this UDL, first one, what will be the load? Load will be W into L. Now where that load will be acting? At this centroid. So what will be the distance, perpendicular distance? It will be this distance. It will be L by 2. So W into L into L by 2. That is the moment due to this UDL. Minus RB into, what is the distance, total distance? This is the point we have considered. RB into L. This is equal to 0. Therefore, RB is equal to WL by 2. So, RB is equal to WL by 2. RA is equal to again WL by 2. Again, you don't have to really write these. Just understand it's a symmetric loading only. Because the load is throughout the beam. Therefore, the total load is W into L. Therefore, since it's symmetric, it will be WL by 2 and WL by 2. So, just to understand only, I have done this. We will be getting that only. Now, I have to find out the bending moment. So, we know that the bending moment at these 2 points, A and B, is 0. For a simply supported beam, this is 0. Now, I have to find the bending moment at the center. Okay, I am considering this center. What will be the bending moment? Okay, so here, the center I am considering a section like this. Okay, so I can either take to the right of the section or left of the section. Anyway, both the sections are having equal type of load, equal only. So I am taking to the right. Okay, so right of the section, what is the first load? W into L by 2. W into L by 2 into, this is the distance. That is again L by 2. L by 2. That is acting in the clockwise. Left of the side is anti-clockwise. So I can take this as positive. Minus. Again this, due to this UDL, that is half is there. That is load is W into L by 2. So I have to consider this loading. Now, where load will be acting at the centroid of this area, of this line. So it will be acting at a distance of, where it will be acting half of this rectangle base. That is, half means L by 2 by 2. That is L by 4. So simplifying this, you will be getting the moment at the center as I am taking this point at C. That moment is equal to WL square by 8. So this is the WL square by 8. So this is the maximum load that is coming here. Now here I have to join this using a, since it is a UDL, I have to join using a parabola. So I will be joining like this. It is not a straight line, but it is a parabola, parabolic variation. It is again positive. So this is my bending moment diagram. Bending moment diagram for a simply supported beam with a uniformly distributed load. Again, one more thing I have to draw, that is the shear force diagram. So shear force diagram, again I am starting from this end. So here RA, what is the RA? WL by 2. It will be like this. It will be moving upward. So here the value will be W into L by 2. Now, what will be the shear force here at the next point? I am considering a small point here. Okay, at a distance of 1 meter. A small point I am considering at a distance of 1 meter. So what will be the shear force here? There is WL by 2. Again, this UDL is acting downward. Therefore, how can I take this WL by 2 minus this is 1. That is 1 in W into 1. So what will be the answer? WL by 2 minus W. Okay, so at each point the force is changing. Okay, so instead of 1 I am taking it as X meter. I will be taking for a generalization. So X W into X. Therefore, what will be the bending moment? That is W L by 2 minus X. That will be the force here. So here it will be reducing. Here the force moment will be what will be at the center. We can just understand the bending moment at the center. What will be that is at L by 2. At L by 2, what will be the bending moment? What will be the shear force? So here, if I am taking the section to the left, what are the forces? Here I am having WL by 2. That is in the upward. Minus, what is the load? W. WL by 2. That is 0. So at the center, the shear force is 0. Again, if you are considering to here, last section it will be minus WL by 2. So I can join like this. Okay, so we will be doing some numerical problem, then you will be able to understand it so clearly. That's the reason why I first of all for the point load I done with the started with the numerical one. Now we will be doing it. Okay, you don't have to worry. So just understand, this is the shear force diagram of a simply supported beam with UDL. So just understand, this is the answer. That is, it is joined by using a straight linear line. Because why it is varying? Because at each point there is load. But whereas in the other case, here what was happened here, just understand, here from point A to C there is no load. That is the reason why it is constant. Okay, so likewise we can find out this answer. Okay, so we will do one numerical problem which consists of this two type of load, so that we will be very easy to understand. Okay, from that we are having some interpretations are also to be made. So just quickly to one problem. So considering a simply supported beam, it is having loads as shown this figure, having these many type of loads, that is 10 kilonewton, 5 kilonewton, and here it is having a 10 kilonewton per meter load is there, and the distances are 2 meter, 3 meter and 2 meter. Okay, so the total span is 7 meters. So I have to find out the shear force and bending moment diagram. Okay, so that is a question. So the first step will be, we have to find out the reaction. So I am just marking the points A, B, C, D. Okay, I have marked the points. So first of all I have to find the reactions as RA, here it is RB. Therefore step 1, that is the reaction. So first one, again using RA plus RB. RA plus RB is equal to, what are the download loads? 10 plus 5, and an UDL is also there. What is the load? 10 into 3. 10 into 3, that is a load due to UDL. So total load will be 15 plus 30, that will be 45. So this is our first equation. Okay, RA plus RB is equal to 45. Now we know that moment at A and moment at B is equal to 0. So moment at A and moment at B is equal to 0. So I am considering sigma MA is equal to 0. This is taken. So I am just taking the equation here, point MA. So now I have to find out the moments. From first, what is the due to the moment due to this 10 kilonewton. So if I am considering a pointer like this, how the pointer will be moving? This will be pushing that pointer to downward, clockwise only. Okay, that is 10 into, the perpendicular distance is 2. 10 into 2 plus, again this due to this UDL. So this you have to clearly listen. That is what is the load? Load is, first one, load into perpendicular. First one I have to write the load is 10 into 3. That is the load. This 10 into 3 will be acting where I am marking. It is assumed to act at the center of this. That is 1.5 meter. From here 1.5 meter, this total load will be acting. That is our assumption. Equivalent load will be acting at 1.5. So what is the, so this is the load. That into is perpendicular distance. What is the perpendicular distance? 2 plus 1.5. Okay, so this is the moment due to UDL. This is the total moment. There is a load into perpendicular distance. Then again plus next one, it is 5. So again I am taking 5 into, what is the perpendicular distance to this? 2 plus 3. So I am just writing to understand only 2 plus 3. Okay, minus Ra, it is to the upward side only. This will be acting to the upward. This will be moving to this side. That is Rb into total distance is 2 plus 3 plus 2, that is 7. This is equal to 0. So this equation you have to clearly understand. So by simplifying, what will be the answer? That is 20 plus, there is 20 plus 30 into, again it is 3.5, 30 into 3.5, again plus 5 into 5 into 5. Okay, that is 150. So total it will be 150. 150 divided by 7, it will be 21.42. So Rb will be 21.42 kilonewton and Ra will be 45 minus that is minus 45, that would be 23.57 kilonewton. So we have find out the forces. Okay, only the important thing you have to understand, it is this value. This is the moment at A due to the UDL. So this thing you have to understand. 10 into 3 into 2 plus 1.4. So any doubt you can ask. Okay, so that is the thing you have to understand. Moment at A due to UDL. Okay, this how it is obtained, you have to clearly understand. So from this, so I have found out the moment. So I am just now marking the different moments, forces which we have obtained. That is Ra and Rb. So here Ra, it is so value of Ra is 23.57, Rb is 21.42. it is there. Here there is 10, here there is 5, and also here we are having 10 kilonewton per meter. Okay, so I'm just first of all step 2, I'm going to find out the shear force. So either you can write the shear forces, or you can just first of all starting drawing also you can start. First one, shear force at A, it is positive only, plus 23.57. So just start from here. Since it is upward, you can just draw, that is 23.1. Just draw a line, that is 23.57. Then just look here, there is no load up to this point. Therefore here there is another load is there. What is that? 10 kilonewton is acting downward. Therefore shear force at C is equal to 23.27 minus 10, that is 13.27. So here we are obtaining 13.27. Up to this point I am marking. Now again, now we are having again the load is there. So I can find out the what will be the shear force at this point, that is shear force at D. So shear force at D is equal to, so shear force at D, it is equal to 23.27 minus 10 minus, again this 10 is there, 10 into 3. So I will be getting minus 16.43. So here the value will be minus 16.43. So here I am getting minus 16.43. Again, what is the shear force at B? It is given as 21. Since it is upward, there you have to take as minus 21.42. Okay, so I am just marking the points here. It is there. Now here it is minus 16, minus 16. So here a small thing is also there. That is, here I have taken 23.23 minus, this is taken from which side? This is considering to the left side. that is taken. So left shear force to the left here is minus 16. So here I am just marking to the left. Again here again shear force at D to the right, if I am considering, what will be the value? If I am considering to the right, the value will be minus 21.42 plus 5, that is minus 21.42 plus 5, that is again it is taken as 16. We will be getting, so either you can take, so here left while considering the value will be, so shear force on the left, that is considering the left side of it is minus 16.48. Now here the shear force to the right, if I am considering a small section, considering a small section to the right, it is again another minus 5 is also there, that is minus 16.43 minus 5, that is minus 21.42 kilonewton. That will be the shear force. So there will be two shear forces, because the what is the reason? Here there is a load. Under a load there will be two forces. Here also you can see. Here again there is two forces. Okay, that is the reason. So again, so here and last one, it is a shear force at B. It is clearly given as minus 21.42. Here both the values will be same. Now we are just marking this force as, so here we are having two forces. First one, it is 16 point, so here I am marking, it is 16.43, nearly 42 kilonewton. Again that is changed to 21.42. okay, then here it is coming and you can join like this. So and this can be joined in a straight line. Okay, so this region will be positive and this region will be negative. So here I can write the shear force here as this is 13.27. okay, so a little bit of confusion may be obtained, but just may be there, but just it is easier. Just understand, I will be telling once again, that is from this force itself you can draw. So the best way it is that just draw a baseline. Now here we are having 23.57. So 23.57, it is going upward. Now again there is no load up to this point. Then from that point a 10 kilonewton, you can see here a 10 kilonewton is acting. I am just marking the guideline. So here it is 23.57. So 23.57 minus 10, that will be 13.57. Here it will be 13.57. okay. Now here having a UDL. Now again you can once again, if you can draw from this side also. This side it is upward, means it should be down. Okay, that is 21.42. Again that is constant up to which point? This point. It is a constant. So it will be constant up to here. Again a 5 kilonewton is acting. So that 5 kilonewton is in the downward direction. Therefore 21.42 minus 21.42 plus 5, that is 16. Minus 16.42, and you can just join with like this. Okay, like that also you can draw. That is always below the UDL it will be a linear line, and for a concentrated load it will be a constant line. So that is the only thing you have to keep in mind while drawing. Okay, so like this you can draw the shear force diagram. Okay, so shear force diagram can be drawn like this, that is shear force at A and shear force at A, then shear force at C, D, and each shear forces. Okay, so here here while writing shear force at A is 23.37. Now shear force at C, it is here 23.27 minus 10. Here it is considering to the left of the section. Here it is considering the left, that is 13.27. okay. sorry, 13.27 while considering the right of the section only. That is, here while considering a load, there are two sections. One is to the right and one is to the left. If a left I am considering, there I am having only 23 point. That is happening here. If I am taking to the right, small section to the right, then what is there? This 10 kilonewton will also be there. That is 23.57 minus 10. Okay. So some more clearly you have to write. Then I am just writing in that way to be more easier. That is here. First of all, we are finding out the shear forces. Shear force at A we found out. Now shear force at C. This is our point C, and that to the left. I am taking to the left. To left means this line. Towards the left, just understand what are the forces to the left? Only 23.27. So towards the left it is 23.27. Now I am considering the right also. Why I am considering two forces? Because there is a force acting. Therefore, I have to take the left and right. And when I am considering right, that is a section to the right here. This section is considered. This right and left is different from what we have said earlier. That is right. What are the forces now to the? This is the section I am considering. To the just right. So what are the forces? 23.57 and 10 is there. So 23.27 minus 10. That is 13 points. So at the same point we will be having two shear forces. Similarly here also. So that is the only thing you have to. Here this is not the right. Here you can. This one is not similar to that we have written here. That is. So in this case here we have written right and this means right of the section. Here what I have considered, here what I am taking is that it is the right hand side only. That is, this section is considered right to this section. This is left. Likewise, only right and left is considered. Okay, this is only taken when we are having a load. So here the shear force is changing its sign. No, not changing the sign. It's the same point itself. It is having two shear forces. So that's the reason why we are writing like this. Okay. So similarly, this is the thing which I have said. That is here you can look at a point D. There are two shear forces, 21.42 and 16.43. How I obtain 21.42? By considering to the right, the loads, considering a section to the just right, and 16.42 is just to the left by considering this. Okay. So likewise we can find out the shear force diagram. Now next is the bending moment. Step 3 is the bending moment diagram. Okay. So in order to find the bending moment, that is the last thing we have to do. For we are having what are the bending moment at A is equal to 0, bending moment at B is equal to 0. Okay. So we are having two sections. First, that is bending moment at A and bending moment at B is equal to 0. Now again we have to find the bending moment at C and D. At these 2 points we have to find the bending moment. Okay. So now so this is C and this is D. So bending moment at C, MC. So I am considering either I can consider now it is the loads to the left or loads to the right. So I am just to the left, only one load is there. So I can take that one to the left. So what is the load? It is there 23.57 into 2. That is my answer. That is 23.57 into 2. So that is 47.14 kilonewton meter. So MC I got. Again I need MD. MD, that is to the right. That is right because I am having only one load. Either you can take to the left. If I am taking to the left, I will be having 3 loads. 23.57, 10 is there and a UDL is there. So it will be easier to find out to the right. So always while finding the bending moment, take the section which is having lesser loads. Take the right, if it is having lesser load, take that one. That is 21.42 into 2. So the answer will be 21.42 into 2, that will be 42.84 kilonewton. So I am having here 47 and 42. Okay, so this one it is 47.12 and 42.84 kilonewton meters. Okay, now how can I join this? So here, since there is here you can understand, since there is no load, only constant load is there, here you can join by linear line. Okay, this is joined by linear line, and here this is under the UDL there will be a parabolic variation. And one thing you have to understand here is that here we have obtained different bending moments. One is 47.2, then 42.84, likewise. But we really don't know what will be the largest bending moment. Okay, maximum bending moment we have not obtained here. So the most important thing you have to understand is that maximum bending moment happens when the shear forces changes its sign. So when the shear force is changing its sign means changing from positive to negative. So here negative to positive. So here you can understand this is the point. This is the point where the shear force is. So under this point only. So if I am just drawing a line, under this point the shear force will be maximum. So I can join my this two lines by like this. Okay, this is a parabola, and this will be the maximum bending moment. Okay, so this maximum bending moment I have to find out. So that is our aim. So the maximum bending moment, so this the point you have to understand is that is the writing here, that is the maximum bending moment is at the point where the shear force changes its sign, that is from positive to negative or vice versa. So this is the main point you have to keep in mind. Okay, maximum bending moment is the point at which the, so now we have to find out what is the maximum bending moment. Okay, in order to find out the maximum bending moment, we have to first find out this point. So at the maximum bending moment, so first of all we have to find out the maximum bending moment. So just drawing a line to find out the maximum bending moment. I have to find out the maximum bending moment. In order to find out the maximum bending moment, first of all I have to find out the point. So here I am just choosing this point as, so this point, this distance, I don't know this distance what it is taken as x, but I am having this distance, it is 2, this 2 meter, this I am not having, this distance I don't have. I just taken an arbitrary value. Now I am going to find out. So the maximum bending moment takes place when shear force, what is the value of shear force here? It is 0, that is it is changing the sign. So maximum bending moment takes place when shear force is equal to 0. So I am just, if I am able to find this x, then I can easily find out the bending moment. So first of all I have to find out that I am choosing the distance as x. X is chosen from this point only. Okay. Now from this I am finding out the shear force at this point. Okay. Shear force at this point. I am taking either, so the shear force at let that point be xx. So shear force at xx, that will be equal to 0. Now shear force at XS can be found out either to the right or to the left. You can take the forces to the right or to the left. I am taking the forces to the left now for simplification only. So shear forces at XS to the left. What are the forces happening? Here we are having 23.57, that is the upward only. I can take it as positive. 23.57 minus this 10 kilonewton. What is 10 kilonewton is happening to the right left side, 10. Then minus again the UDL is there. That UDL, it is having a value of 10, right? What is the value of UDL? That is 10. Therefore, so I will be drawing once again a clear figure. From this figure you just understand here. I will be just drawing the figure so that it will be some more clear. So this is the loads which are happening. So this is the section. This is the section where I am choosing. This is the section where this is the X. At this point the shear force is 0. So I am going to find out this. This is 10. This is 23.57 and this is 10 kilonewton per meter. Therefore shear force at this point should be 0. Therefore 23.57, it is to the up, minus 10 minus another load is due to this UDL, that is 10 into X. This should be 0. That is 23.57 minus 10 minus 10 into X is equal to 0. So what will be the value? That is 23.57 minus 10, that is 33.357 divided by 10. That is the value of that is will be having 23.57 minus 10, that is 13.57 divided by 10, that is X value is equal to 1.357. So from that, so we have obtained, that is here. So this is the point where the shear force is 0 and the value we obtained it as 1.37. So at this distance the bending moment is 0. So now we have obtained the value. So now just we have to find out the bending moment at that point. Okay. So again coming into the figure. So here this is the, so here we have obtained X. X is equal to 1.37 meters. Now we have to find out the moment, bending moment at this point. Okay, so I can either take the forces to the left or right. So I am taking to the left, I am again taking. So that is bending max, that will be the maximum bending moment. Maximum bending moment is equal to, so this is to the upward, that is 23.57. So what is the distances? I am just marking the distances. Since I have obtained distances, I can mark here. So this distance is 2 meter. This distance is 1.37. Okay. So what is the value of 23 into this distance? 23 into 2 plus 1.37. That is one load. Minus this 10 is happening in the clockwise direction, anti-clockwise direction. That is minus 10 into 1.37. Again minus due to this UDL, it is 10 into 1.37, that is a load, that into where that load will be acting at this center, 1.37 divided by 2, 1.37 divided by 2. So this is the thing you have to always, this by simplifying this you will be getting the answer, that is it will be around, that is 23.57. So the value will be, by simplifying the value will be 56.34 kilonewton meter. So this will be the maximum bending moment. So that will be happening here. That is the maximum bending moment, that is at this point it will be 56.34. Okay. So the maximum bending moment is happening at this point and the value is obtained. So this is positive. So this is our final bending moment diagram. So here this is a linear line, this is a linear line, and this one is parabolic. So finally coming into this figure, you just understand. So this is a parabola. Similarly, a similar problem it is done in your note which I am going to give here. You can understand here a similar type of, just some other wordings are only. This was the shear force which you have obtained. So now here you can look here. That is, this is the bending moment diagram. So here this region we are having a straight line. This region again you are having a straight line, and this region is a parabolic region. That is below a parabolic, below a UDL there will be a parabolic variation only. Okay, so the only thing you have to understand is that the shear force will be maximum when there is a bending moment is changing its sign. Okay, for example, here a simple load is given. Here E is the point. So at this point E, this is the point where the shear force will be maximum. Look at here. That will be, again they have found out the value, something around 56 kg. So that is the only thing extra you have to do. So in order to find out that point, what we have done, we have to choose an x, then we have an x arbitrary distance is chosen. From that we are finding out what is the value and everything. Okay, so this is the way in which you can draw the shear force and bending moment diagram of a simply supported beam. So in the coming sections we will be handling some more problems with this. Okay, so that's all. Thank you.